Xiaofeng and Hui-Chang, so they will.
Yes.
Okay,
Oh,
now
yes.
let's started. Okay, okay, very good. So let's start. So today's talk, and so we are happy to have M Pawlowski of Heidelberg University, and he's telling us about the functional renormalization group approach to the phase structure of QCD. And so let me briefly introduce today's speaker, M Pawlowski. Yeah, in fact, I have a brief CV, but maybe no need to read it. So the Yang is already quite well known to our community of heavy-ion collision. So he's actually a big authority in the field of functional RG approach, not only for QCD, but also for quantum gravity and condensed matter physics system. And there are lots of similarities between QCD studies and condensed matter studies. And so such kind of interdisciplinary knowledge is quite valuable for our studies. So so today, so Yang is telling about their first principles approach to the QCD phase structure from the functional RG. So we have actually the time for discussions after the talk, and so during the talk, so you can ask a question. But if the discussion or the question takes time, then I might interrupt you. But please keep in mind we have time for discussion. So please, Yang, start.
Yeah, thank you very much, Kenji, for this very nice introduction. Of course, what you have said about authorities is not in my brief CV. And I would also, to iterate what you said about discussion, so if you have questions, please ask them immediately. And of course, if it's too long, then certainly Kenji will stop you. So what I would like to talk about is our results on the phase structure of QCD, and also observables like fluctuation observables with first principle functional QCD. And I first also would like to tell you why we think that this is a first principle approach. So I have to walk you through some technical details, but of course, at the very end, the interesting results will be on the phase structure and on respective observables, which can be also measured in the heavy-ion experiments. So most of what I will tell here is on behalf of the fQCD collaboration. It's a functional renormalization group, QCD collaboration. Let me also briefly, if I can, introduce the members of this collaboration. It's hosted in Brookhaven, Darien, Darmstadt, and Heidelberg. And the current members of this collaboration you can see here. And I will also refer to the respective results when I come to it. Okay, so just a short outline of the talk. It's 1 hour, so it's good to know where we are heading towards. So what I would like to explain first is how we get our hands on correlation functions in QCD with functional methods. It will not only be the functional renormalization group, but also Dyson-Schwinger equations. And actually a comparison of these two similar but different methods will also be one of our reliability tests for our results. And after I have hopefully convinced you that this is a method one can trust really for correlation functions in QCD, I would like to talk about applications. First of all, the main one is the QCD phase structure, in particular at larger densities, and then also looking at observables like fluctuations of conserved charges. And if there's still time left, so if there are not that many questions or I'm racing a lot, then I also would like to talk about non-equilibrium processes in the phase diagram. Okay, so the respective results, that's already a plot I would like to explain. We see also here, these are our results for the phase structure and also including the critical endpoint. I will discuss also how reliable these results are. There will be results on hyperfluctuations in comparison with new star data. And if I have time, I will also tell or discuss equilibration times, which we have in particular at higher density. Okay, but first you have to bear with me a bit of technical details because I would like to really tell you as well as possible what we are doing and how to assess the reliability of our method. So the functional methods are mostly concerned with generating functionals in QCD. The one we are looking at is the effective action. So you can think about it as the free energy of the theory in a given background. You can also switch on magnetic fields or chromomagnetic fields, electric fields, whatever. So this phi just stands for the chosen background. And the functional renormalization group is a method which starts by suppressing all infrared modes in the theory. So let's assume we suppress all quantum fluctuations for momenta below 20 or 90 GeV. And then, of course, we have a very good grip on the method, because then we talk about perturbative QCD. We can compute the effective action in a systematic way in perturbation theory. And that's our starting point. So we will start at a very large scale, at a very large momentum scale with perturbative QCD. And then we will just successively remove this infrared cutoff. And this will be done by the flow equation. So we take a differential step here in the cutoff step, infrared cutoff, which means we're integrating out momentum shells one by one. The equation which governs this is the flow equation or Lattice equation, and this is a one-loop exact equation. So let me walk you through this. So here we have our free energy. That's the object where all the infrared modes are suppressed. And the dt is just the logarithmic scale derivative with respect to this cutoff scale here. And this free energy or ground potential reacts by a bunch of one-loop terms. So this is not an approximation. This is exact. However, these propagators here, so here you see a gluon propagator, this is the full two-point correlation function of the theory. It's not a perturbative propagator, it's a full correlation function of the theory. Now here you see an object which is actually the ghost. So this already indicates we are looking at gauge-fixed correlation functions. I will also say something to it later, why this is actually, in my opinion, more an advantage than rather a liability. We have the quark quantum fluctuations, and there's something special to the approach here. We introduce hadronic degrees of freedom as effective fields. So we are not going to an effective theory. We are just changing the parameterization of our theory, and that makes some bookkeeping and computations far simpler. Okay, so the important point here, this is closed. So I have not left out some terms. This is a closed one-loop equation. However, it's a very complicated one because these are the full correlation functions in the presence of this very general background. Okay, there is a similar equation, the functional Dyson-Schwinger equation. You see already there are similarities. Well, here are two-loop terms which are not present in the functional renormalization group equation. That comes from the fact that the functional renormalization group equation tells you something about the scale dependence of the theory. So it's a differential equation, while the functional Dyson-Schwinger equation is the full quantum equations of motion in a given background. So this gives us these two loop terms. Okay, but in both cases, we can already see these functional relations look quite similar in this diagrammatic form. And what we are doing now is we're computing correlation functions from it, and we aim at apparent convergence. What does it mean? We take a bunch of correlation functions, which of course lead to, in the case of the functional renormalization group, to a set of coupled integral differential equations, which we have to solve. And then we toss in further correlation functions, higher order correlation functions, and look whether the results for the lower order correlation functions converge if we go to higher and higher orders of the approximation scheme. That is how we check that our results are really trustworthy. That's one of the checks, and the other one I already have mentioned. We do this with the functional renormalization group, we do this with the functional Dyson-Schwinger equations, and then we compare results. Okay, so how do we do this? How do we come from this equation here to correlation functions? So you see already that if I look at the gluon here, there is a two-point correlation functions already in there. So what we need is the gluon propagator. So the two-point correlation functions of two gluon fields. How do we get this? Well, we have this equation here. We take two derivatives with respect to the gluon. That gives us the inverse gluon propagator, and we get a differential equation in terms of this cutoff scale here for the gluon. That's this equation here. So again, the details are not that important. This is the gluon propagator, the inverse one, and here is a bunch of one loop diagrams. Again, this is a closed equation. There will be not more diagrams. This is now in pure blue. I have left out these quantum the meta corrections here in order to keep it relatively simple. Okay, but what you immediately see is, well, in order to compute this object here, we also need the ghost propagator. We need the full gluon 4-point function. We need the full gluon 3-point function. So there will be other equations which are coupled to this. And if I go to the higher equations, they will couple to even higher correlation functions, and so on and so on. This leads us to an infinite hierarchy of equations. So that was the gluon. Of course, we also need the quark propagator because it's running around here. We not only need the quark propagator, you have already seen there will be vertices. So for example, we need the quark-gluon vertex. And the quark-gluon vertex is a very important function if it comes to computing the quark propagator, which is, as you can see here, an essential ingredient in the approach. The quark-gluon vertex is not like you're used to in perturbation theory, just gamma mu. It has 8 tensor structures which go into these equations, and these 8 tensor structures depend on 2 four momenta. So it's a very complicated object, and actually that is one of the things we have computed fully and which gives us reliability in our approach. We also, of course, need quark-antiquark scattering. So you see it's getting more and more complicated. This object here, of course, for example, in 2-flavor QCD, has 10 independent tensor structures. In 2+1 flavor QCD, 27 momentum independent tensor structures, and so on. So you see it's getting quite quickly complicated, but we have to just compute it in order to get reliability. So for this system here again, you get diagrams. And again, for example, here we have the inverse quark propagator. So this object here, and its scale change. So we do one infinitesimal momentum step. Cutoff step is related to a bunch of one loop diagrams. And all these one loop diagrams only take momenta at about the cutoff scale. That is what this cross stands for. But again, you see this depends on the quark-gluon vertex, on the gluon propagator, and other quantities. So these, of course, now have to be computed. Now, what you presumably have not seen is this object here. There's something new going in, namely this dashed line. That's not the ghost. That's actually this object here. So what is it? What we have done is we have taken a full 4-quark vertex, so this object here, and we have written it as an S-channel exchange of a quark-antiquark state, a scalar pseudoscalar state, plus rest. So we have not dropped the rest, we keep it, but we can just reparameterize our full 4-quark scattering as an S-channel exchange plus rest. And that's how we introduce our effective fields. And of course, also these effective scalar fields, now scalar and pseudoscalar fields, you can interpret them as pions and sigma resonance, obey their own flow equations. So that's just a bookkeeping device. It does not mean we are going to an effective theory. It simply means we are rewriting the full quark-gluon correlations with our bookkeeping in a more convenient way.
Yeah.
Okay.
Yeah. So there is a question in the chat exactly on this point.
Yes, unfortunately, I cannot see the chat. I don't know how to
Yes, so let me read it. So yeah, the question is, any double counting between the gluon and the hadronic fluctuations? That is the question.
That is why I have this line here. So we have, before we introduce this field, this is the full 4-quark scattering state. So this is a vertex which we have to compute, this object here. Okay. Now we rewrite it in terms of an S-channel exchange of a composite field plus the rest of the vertex. This is an identity. Okay. And now we fix this uniquely by saying all the S-channel exchange should be in this process here, which means that the rest, if I go to the S-channel, is 0. So that's a unique distribution of the full fluctuating 4-quark scattering vertex in terms of an S-channel exchange plus the rest vertex. There is no double counting. Of course, I have cut this a bit short. I mean, there's formalism behind it, and you have to trust me. We can go through this in detail.
Yeah, but that is actually the quarks, right? But the question is about gluons, because the quantum fluctuation should involve gluon fluctuations as well, and so
it does.
Excuse me?
These processes are gluonic fluctuations. At the very beginning, this process, if you go to large momentum QCD, there is no four-gluon vertex, four-quark vertex. This is gone. This is gone. The only process left is this one here. That is the process which generates this coupling in the first place.
Mm-hmm.
Okay? So there's no, first of all, there's no double counting. And second, of course, all the processes we have here are generated at large momentum scale, so perturbatively, if you wish, by quark-gluon processes. After sorry?
So your hadronic fluctuations don't include glue balls?
Well, they do include glue balls. Like you have glue balls in Lattice QCD. I mean, what you integrate over in Lattice QCD are quarks and gluons, and that's what we're doing here. The path integral which stands behind this is one with quarks and gluons. Okay? So where you would see the glue ball, keep in mind, this is a Euclidean formulation, and the glue ball is far off its on-shell condition. Where you see it, for example, is in the four-gluon scattering vertex. If you go to time-like momenta there, and we are doing this at the moment, then you should see the glue ball resonance. Okay? But keep in mind, there's a very, if you go to Euclidean space, there's a very efficient scale ordering here. You come from large scales, and at the cutoff scale where all these resonances are forming, which is about the scale of a couple of 100 to MeV to 1 GeV, all of them, except a few, are already very heavy. So which are the resonances that still can contribute? Of course, the pion, because it just has 140 MeV, the sigma a bit, and the quarks, of course, because they have constituent quark masses of a couple of 100 MeV. But most of the other hadron resonances are simply out by their mass in a Euclidean setting. If you now want to look at the resonances, then this is different. Okay? So, and keep also in mind, I don't have to do this. I could just simply stay in the quark-gluon writing, but it does not make the things more less difficult. Okay, so if you have resonant degrees of freedom in your Euclidean scale setting, it's better to take them into account within this process. I will also say a few words later. So if at the very end this is not clear to you, maybe we come back to this. Okay, so let's do this in vacuum QCD first. And now it's very important for me to say this because I hear this again and again in talks. We have to fix parameters by QCD. No, we don't. So what I'm doing now here is I report on results. That's vacuum QCD. I mean, that's what we need later also at finite density. And the input are the fundamental parameters of QCD at a large momentum scale. And typically we take 20 GeV. For the really accuracy runnings, we go to 100 GeV and then they go down. So what are the input parameters? It's alpha S at the scale. And it's the current quark masses. So if you go to two flavor QCD, we go into the strong isospin symmetric limit. So the up and down current quark masses are the same, and they are tuned such that we get the right pion mass. If you go to 2+1 flavor QCD, of course, the same parameters are there. And the other parameter we have is the ratio. And I see it's, sorry, I made a mistake here. It should be M strange over ML and not the other way around. So M strange over ML at this cutoff scale is 27. Okay, so the only parameters we put in are the fundamental parameters in QCD. Everything I'm computing now or I'm showing you is a prediction. Okay,
So in order to get really to predictions, we have to do a lot. So this is our current set of correlation functions we consider. We consider the full gluon two-point function. We consider the full Gauss two-point function. We consider the full Gauss-gluon vertex. We consider the momentum dependence of the classical tensor structure of the three gluon vertex. There are further ones. We know that they are suppressed. And we compute, again, the classical tensor structure at the symmetric point of the four gluon vertex. There are also checks that this is a quantitatively reliable computation. We compute the full quark two-point function, the full all A tensor structures which we need here, full momentum dependence of the quark-gluon vertex, and then there are higher vertices which we have to take into account in order to respect gauge invariance. And then we have this effective field, and the only fields we take here are the scalar and pseudoscalar resonance. They have propagators. We also compute these propagators. We compute the Yukawa vertex, which scatters the quark and antiquark into these composite fields. And we compute arbitrary scatterings of, or actually up to 12 in this specific computation, scatterings of these resonant channels with the quark-antiquark again. So this is already a very elaborated computation. All of these correlation functions you see here, and if you see such a vertex, it's not just one tensor structure. Here, for example, it's 10 tensor structures, momentum dependent. All of these correlation functions feed back in their respective flow equations. So it's a really large set of coupled differential integral equations. Okay, and we are doing this because we're aiming at apparent convergence. So what we want to see, if we are now going one level in our truncation higher, nothing is changing anymore. Nothing means relatively nothing. Okay, let's look first at results. These are our results for the two-point function of the gluon. And what I'm plotting here is momentum squared times the propagator. That's the momentum that has momentum scale 0. So it's really the thing which goes into observables or even in the integrals. And you see this is in comparison to lattice results and to flavor QCD. It's bang on. Here, the lattice levels off. That's a discretization artifact. These results are not continuum extrapolated. So that's a lattice artifact, not an artifact in our computation. Here we see perturbation theory. So this result is bang on. And I remind you, this we get by taking the strong coupling of QCD at a large scale and the current quark masses. That's our input. Here you see the same for the quark mass function. You see also our area estimate. This error estimate is a combination of seeing how well this converges, and of course our estimate for the systematic error. If you are interested in this, we can discuss this later. Okay, so in my opinion, one sees very nicely that we are up to the task in vacuum QCD. And on top of this, this momentum dependence is fairly simple. This is important for us because if we would have complicated correlations, which of course we have in the presence of resonances, that's one of the reasons to introduce these composite fields, then of course it's getting more complicated. Okay, another very important ingredient, that's why I want to flash some results, is the quark-gluon vertex. Keep in mind it has 8 tensor structures, and all these tensor structures have momentum-dependent dressing. So these dressing depend on 2 4 vectors. Okay, so how does the result look like? So maybe again, you can expand this with tensor structures, and we are talking about the dressings of these tensor structures here. This is a result for the leading tensor structure. That's the classical tensor structure gamma mu. These are different snapshots because we have 2 4 momenta, and which can be seen as radial momenta and angle. So we look at this at different angles. What is important here is not only that we get a result, it decays nicely for large momenta, but again, it looks very simple. You can go to other tensor structures. What I have put down here are the 3 tensor structures which are really dominating the physics here. One can now show which tensor structures are important or not important in order to get the results. And these three tensor structures are important. And these tensor structures we also need if we go to finite density. So how it looks like, again, is not that important. What is important is these are relatively simple correlations. That's good for us. As I said before, if we have resonances, we have to take special care of them. Okay, so that's one of the reasons why we trust our results and we trust in our apparent convergence. There are similar results, in particular for the leading tensor structures. I flash here a couple of functional results, not only in Dyson-Schwinger, in functional renormalization group equations, but also in Dyson-Schwinger equations. And before I now come to finite temperature and density, let me make three remarks, because also the one concerning the glue balls already hinted in this direction. What we have is, in particular, if you go to thermodynamic observables, and if you think about it, also the free energy is something like a thermodynamic observable, we have an off-shell representation of thermodynamic observables, namely in terms of loop. If you want to rewrite this in terms of on-shell states, like you do in the hadron resonance gas, what you have to do is you cut, like a Kutkowski rule, you cut this diagram here, and you put in a sum over all asymptotic states. If you do this, in order to get your hands on this loop, and we know this very well for example, the trace of the quark condensate or similar things which go into the quark contribution to the pressure, you need a lot of states in order to get conversions. You don't need too much here. So for these observables, an off-shell presentation is very helpful. And also this, if you don't believe me, we can discuss this later. Gauge fixing, which I'm using here, so most of the results I'm showing are in the Landau gauge, is a parameterization. And that's why I emphasize that we have simple correlations. So you know that if you have an integral, choosing a optimized parameterization can help you a lot to solve this integral. And in our opinion, the Landau gauge is very well suited to get our hands on these correlations, which are nothing but moments of our path integral. Okay. Of course, there comes a price. I'm a keen supporter of the no free lunch theorem. We have simple correlations, but some of the observables which are interesting, we have actually difficult access to. That does not mean that we can't solve the theory, we simply have difficult access to some observables. Okay, the last one, that if you go to models, please keep in mind if I'm evaluating my effective action on some solution, it's the full quantum equations of motion, quantum equation of motion, so maybe my mean field is not your mean field. Okay, so let's come to application.
Yeah. So
yeah?
Can I ask you a quick question on
Sure.
your first remark? So that is, you talked about these asymptotic states, but this is presumably for matter at finite temperature or finite density. But finite temperature, do you really have asymptotic states?
No, what I'm saying is that we know, for example, from the hadron resonance gas, you need a lot of resonances. For example, you get a good grip on the pressure. And I have been asked this, so if I look at the fermionic pressure, are even simple approximations in models enough to give us this pressure when they don't take into account all these asymptotic states? And the only statement I want to make is, in my opinion, yes. And if you look at the quark propagator I've shown you, and you have the lattice comparison, if you don't believe my results, it's a very simple function. It looks boring, and nevertheless, it gives you the full fermionic pressure. That is the statement I wanted to make. Whether you have or have not asymptotic states, I mean, that's even an additional point. So if you wish, I mean, what you can put in here are asymptotic states at mu and t is 0, which of course makes it even less likely that the convergence is good.
Yes.
Okay.
Okay.
So you're completely right, but I mean, that was not my point. Okay, let's come to results. Now, I hope I have convinced you that what we are doing works well in the vacuum, but now we want to go to finite temperature and density. And of course, an additional complication already at finite temperature is that you get even more tensor structures because you have the direction longitudinal and transverse to the heat bath. So for example, if you look at the 3 gluon vertex, you get just 2 of them, okay? And it gets even worse if you go to higher order correlation functions. So what you like to have now here is an approximation which still is quantitatively trustworthy, but it's a bit, but is simpler, if you wish, than the one you have at finite in the vacuum. So what we are doing now here is we expand our full correlation function. So that would be, for example, the gluon propagator in terms of some given input. And what I will use a lot is the results. That's one of the reasons why I explained them so much in the vacuum for 2-flavor QCD. And then there's the rest. Okay, and this rest carries the finite temperature fluctuations, the finite density fluctuations, and if I expand about 2-flavor QCD, also the strange fluctuations. This means we have a flow equation for this rest, which is given by the flow equation for the input, but that's input, so we have it, and a flow equation of the rest. So these are now diagrams or differences of diagrams, which of course depend on the input. And the delta gamma, so the difference of the fluctuations. So this is now the flow equation for the difference of fluctuations. And now for this difference of fluctuations, in quite some cases, these again are very simple. So I can use worse approximations and still keep my quantitative reliability. Okay, so I flashed this. I don't want to go through it again, which approximation we take here. So we are now talking about 2+1 flavor QCD at finite temperature and density, and we expand this about the quantitative solution we have in 2-flavor QCD in the vacuum. So now we can do the same for Dyson-Schwinger equation, and we cannot only do the same, we have done this, the same, and this is work with Fei Gao, who's a postdoc in Heidelberg at the moment. And what we have done there is, again, we have used input from the functional renormalization group, so the quantitative results for the correlation functions here, and we have put them into our Dyson-Schwinger equation. The new ingredient for this Dyson-Schwinger results in comparison to other Dyson-Schwinger studies is at finite temperature and density that we take into account all 8 tensor structures of the quark-gluon vertex. And as I told you before, we at least need 3 of them in order to be quantitatively reliable. You get the same as before. You have a system of Dyson-Schwinger equation. Now, I mean, the scale derivatives are missing here, but it looks the same. It's a coupled set of differential equations. The next step, actually, just to flash it, which we will do, is we will incorporate these diagrams here, which are proportional to correlation functions we have computed here. Okay, but before we do this, this is the approximation, for example, for the Dyson-Schwinger equation of the quark-gluon vertex we consider. Okay, now there are benchmark tests at finite density, and I will just flash them. So the results you see here is the black line. This is the Dyson-Schwinger result, and the blue line, which is the results we have already talked about. And then in comparison, there are lattice results. So again, we are bang on. These are finite temperature results, so ignore them at the moment. We can go to finite temperature. Again, we reproduce very well the few lattice results which are there in QCD. We can look at the quark mass function. That's at 0 temperature. You see we are bang on the quark mass function. And you see I'm now swapping between functional renormalization group results and Dyson-Schwinger results. They are quantitatively compatible with each other, and they are where we have benchmark results in the vacuum at finite temperature from the lattice. They are also on the lattice results. So they agree with each other and they agree with the lattice results. We can look at the chiral order parameter because that's how we will compute our phase boundary at the very end. We will take the renormalized light condensate. Here again, you see our result, this time from Dyson-Schwinger equations, but here you see the comparison with respect to the functional renormalization group results. And I should mention the functional renormalization group results are results with RHIC Fu and Fabian Rennecke from last year, and the Dyson-Schwinger results are here with Fei-Gao, just very recent ones. Okay, and you see the functional methods are in quantitative agreement with each other, and where we have lattice comparisons, they are also in quantitative agreement with the lattice results. And now keep in mind, I emphasize this again, there is no pheno-parameter. We have started with vacuum QCD, we have put in the strong coupling at a large scale, the current quark masses, and that's it. There is no pheno-parameter here, which we had to fix to get these results. These are predictions. Okay. We can also go to the reduced condensate, which is something also on the lattice is computed a lot. And again, we are in quantitative agreement with here the lattice results from the Wuppertal-Budapest collaboration, but that's a universal agreement. Okay, let's come to the phase structure. So that's the first major result. That's our phase diagram, and what we have put in here are the Taylor expansion results from the Wuppertal-Budapest and the hot QCD collaboration. So you see here at small densities, we are in agreement with the lattice results. So the current results I'm talking about are the blue results. That's the functional renormalization results here. And the dashed results, that's the recent, very recent, so from last month, Dyson-Schwinger results with Fei-Gao. We have also put in another Dyson-Schwinger result of the group of Christian Fischer in Gießen, and I will now walk you through all these results and look at the comparison. So here are the comparison results from Christian Fischer and his group. Okay, so if you look at the most recent functional renormalization group and Dyson-Schwinger results, and I will tell also something about the reliability here, these two endpoints we get are essentially on top of each other. Okay, so if I talk about quantitative reliability, these 20 or 25 MeV differences, I consider quantitatively on top of each other. So we have an error bar, which I estimate, but that's now my estimate, not of my collaborators, to be less than 10%, but 10% is, I think, a good number. Okay, so I will also try to convince you that our computations are reliable up to densities, baryon chemical potential over temperature smaller equal to 4. Above this, we lose quantitative reliability, and I want to tell you also why. Okay, so this is the region we have control over. We don't see a critical point there. And this is the region where we still have to upgrade our computation. So you see our prediction for the critical endpoint is not really a prediction because it is in this area here. However, this is a prediction, no critical endpoint here. Now, let me walk you through this. So what are our reliability considerations? The first is, do we miss something? So we have an approximation, do we miss something here? Now let's look at a very nice FRG study, also a recent one by the group of Jens Braun, part of the fQCD collaboration, where they looked at, that's now two flavor, at a computation in the FRG where you take all for Fermi interactions into account, so-called Firth-complete basis at finite density, and you look at the dominance ordering. You see here, you see, I have indicated this with Q bar Q, expectation value of Q bar Q. Here, the scalar pseudo-scalar channel is by far dominating. In a way, this plot is a bit, it's not irritating, but it's not really telling the full story, even if these channels look out of magnitude. I mean, they are smaller, but not that much smaller. If you switch them off, nothing is changing in the observables. So that's how you have to consider the relevance of a given channel. It's not the strength, it's its impact on observables. So what you have to believe me here, and that's what also is told in this nice paper, is this channel here is by far dominating. If you switch off the others, you essentially stay with the observables you have. Now, at a given density, that's now the core chemical potential over the critical temperature at vanishing chemical potential at about 2. Keep in mind that's a 2-flavor computation. The dominance ordering is changing a lot. So you go from scalar pseudoscalar dominance to diquark dominance. That is actually a diquark channel here. It's a color superconducting channel. So if you translate this in the 2+1 flavor computation, this would actually happen here. But if you make a conservative estimate, you give it a bit leverage and you go to mu b over t is approximately 4. The other thing is that we have, that comes back to Uli's remark concerning the glue ball. For example, what we have not taken into account explicitly are baryons. Keep in mind the diquark channel here is actually related to the baryon, because how a baryon would form is first you get a diquark and then it scatters with a quark into a baryon. And now if you consider, that is a nice paper by Christian Fischer, Gernot Eichmann, and Welsbacher, PhD student of Christian. So if you switch on baryon effects, that is comparing the red and the black curve, essentially nothing is changing. Okay, so that gives us an additional reliability check and reliability support for our computation. But keep in mind, if we go beyond mu b over t is 4, we have to do something. At least we have to check our reliability in U. There's another hint for this. There's another hint for this, and that's this region here, which we have baptized quotation mark inhomogeneous phase. There, the pion dispersion gets a minimum at non-vanishing spatial momentum, and the chiral condensate is sizable. So this you can see as an indication for a mixed phase or inhomogeneous phase. At least it's a technical indication that we have to crank up our approximation here and look a bit more closely in these dispersion effects. So both of this and this tells in converse, our approximation for mu b over t is reliable for mu b over t is smaller or equal to 4. In converse, this means for mu b over t larger than 4, we have to crank up our approximation in order to get quantitatively reliable results. Okay, so that brings me...
Yeah, may I interrupt?
Sure.
Oh, please go back to the previous page. Well, yes. Okay, so yeah, my question is about this diquark dominance. So mu over t 0 over 2 or something. So coming back to my previous question about the asymptotic states. So if I interpret this in terms of the asymptotic states, the dominance of a Q bar Q can be interpreted as the dominance of a mesonic degrees of freedom. And in the same way, I'm tempted to interpret this as some dominance of the diquark excitations, but the diquarks are not gauge invariant, so they cannot be asymptotic states. So how can I?
But I'm not talking, Kenji, I'm not talking about asymptotic states. That's why I made the remark. This is dominance, this is off-shell dominance in the loops.
But
These are not asymptotic states.
Okay.
Okay.
But this could be an argument for the justification of a hadron resonance gas model if I switch this to the dual description, if there is some correspondence, yes?
Yes, but this corresponds. So how would we do this? So first of all, this is off-shell. And what we see is we need these off-shell propagators, a diquark propagator. And as you said correctly, this is not an asymptotic state, okay? But in the loop, this resonance state can propagate, Okay. So now if you, and very obviously, this will have an impact about the asymptotic states you see at these densities, right? So now what we would have to do, we have not done this, is to look at an approximation of our effective action where we allow for more and more asymptotic states and look how they are switched on by off-shell fluctuations. Okay. So this question is very well disentangled by the scale ordering you have in a Euclidean setting. Okay, so if you have, I mean, it's often said, and this, by the way, this baryon effects are off-shell. It's about off-shell baryons. It's not about on-shell baryons. So that's a different story. So which, if you wish, which resonances you see here, right? That's an on-shell question. I'm not saying anything about this with this statement here, okay? So thanks for the question. That should, I mean, I should have said this.
Okay.
That's not saying that we can see diquarks here, which of course, I mean, would be ludicrous in the first place, but I mean, I'm not, and this is also not, I mean, if you would have seen here, baryons are important, it would not mean that we see baryons here, but it would mean that baryon off-shell fluctuations drive physics here. That's also actually one of the reasons why I'm not surprised here that they don't play a big role. Because if you have a baryon loop, you have a baryon and an antibaryon. And the baryon gets close to resonance by chemical potential, and the antibaryon gets away from it. So I'm not surprised about the result, but of course you have to check it. And here again, we are talking about off-shell. Maybe having the expectation value is a bit odd, but it's just talking about the diquark propagator and diquark scattering vertices.
I have a question just to clarify. On the left plot is mu b over t equal to 4. That's corresponding to 1.3 on the right plot, top plot. Is that right?
No, mu b, you have to multiply this by 3. Actually, this object here is, but keep in mind that's also T0, which is 100, would be translated into 155.
Okay.
Right? The other thing is that, I mean, it's a theoretical computation in the chiral limit, but if you want to straight away translate, multiply this by 3 and you're at 6.
Yes.
Then you have to see T0, it's even larger. Okay, but keep in mind in the chiral limit, T0 is 130.
No, I'm trying to say is for mu b over t equal to 4, the left side is still diquark dominant, so that you're calculating.
No. If you take this literally, this is mu b over t is 6. And then you would be out here.
Ah, okay.
So if I take this literally, but keep in mind, I mean, we made a serious investigation about scale translation from 2 flavor to 2+1 flavor. We have to take into account that this is in the chiral limit and so on. That's why I say the conservative estimate from this. So the first thing is we expect that at some mu b over t, the diquark takes over. The diquark is not really part of the approximation we have taken in the FRG. It's part of the approximation we have taken in the DSE. Okay, but nevertheless, if the diquark takes over, we have to crank up our approximation. So if I make just a literal translation, it would mean mu b over t is 7. Then we are here. Then I could say, okay, great for us.
Okay.
But if you now be conservative and you also make the scale transformation from 2 to 1, 2 to 2+1 flavor, you are more in the realm of 4 to 5.
Okay. So
and I don't want to support our range of validity.
Yeah. Okay. Okay.
So I want to be conservative.
Okay. Could I understand the right plot around the 2? Meaning on the left, below 2 is meson dominant, and above that is baryon dominant.
That goes back to Kenji's question.
Yes.
I would naively, yes, because as I said, I mean, you need an off-shell diquark in order to create a baryon. right? I mean, if you don't have very large density, the diquark forming process, in my opinion, is you have a quark-quark scattering into diquark resonance, and then this scatters with a third quark into a baryon. And then having this diquark resonance indicates baryons.
Okay.
So naively, yes, but before I make a solid statement here, I want to see this in a computation where we consider asymptotic baryons.
Okay, thank
I
you.
mean, actually, I have done this with Kenji for quite a while now. There's a paper. It's 5 years now, Kenji's, right?
Yeah, maybe
waiting for public. Sorry?
Maybe more than 5 years.
Yeah, I wanted to be conservative again. So more than 5 years. And of course, that's a very interesting question. Where at the moment, we can't say. But yes, you can take it as an indication. Okay, so keep in mind, this area now is out for quantitative estimates. I have told you from here on, we lose our reliability more and more. We also know that whatever we have, there will be something here. So you can say either no resonant effects, and all the resonant effects either indicate something like color superconductivity resonance or inhomogeneous or mixed phases. So something will happen here, okay? So this, our Z estimate, you should not read as a Z estimate, you should read as an estimate that something interesting is going on in this region here. So that's my prediction from the results we have. As I said, from here on, no quantitative reliability. So this region is not quantitatively reliable yet, but from the combined analysis, something is going on in this region here. And I call it now a Z estimate, but as I said, it's something interesting is going on, and we are on it in order to crank up our approximation here in order to get reliable estimates, so stay tuned. Okay, I want to, since I'm heading towards the 1 hour, I nevertheless want to say something because I saw this plot here in the nice talk of Xiaofeng Lu, and I want to say something about it. Of course, this is let's say an update of the old Stefanov plot. And those of you who discussed with me in the past know that I even didn't like the Stefanov talk in the first place, because I think it tells the wrong message. So what we have here is this usual scatter plot of results from lattice QCD and functional methods and low energy effective theories on the position of the critical endpoint. Now, before I go through them, a disclaimer. Most functional computations, low energy effective theories, or QCD are not set up for Z predictions. They are set up for different purposes. They usually offer also the critical endpoint location, but they are not set up for this. Okay? So now I will go through them and throw out all of them, which cannot make a prediction for the critical endpoint. Now, another disclaimer, it's very important for me, because if you wish, I mean, I'm here in 2 results, but I have worked in models here, so my results scatter for the critical endpoint, scatter this plane, okay? And I don't want to say that my computations are not good, but they were not set up for the critical endpoint. So lack of predictive power for Z predictions is no quality measure for papers, okay? So let's go through and remove those papers that are not made for Z predictions. And I have now 3 quality markers with which I want to remove them. The first is old Zs. If there is an old computation which is outdated, we remove it. Okay, that is for lattice QCD, for functional QCD approaches, for low energy effective theories where updated computations are available. The second is low energy effective theories and functional results, so QCD computations in qualitative approximations that miss lattice benchmarks at vanishing chemical potential are out. So if some computation does not match the lattice curvature at zero chemical potential, it will not be good in giving us a prediction for the critical endpoint. And you see these 2 points already remove everything which is here. And that's actually not new. Also I think the original plot is from 2004, if I'm not mistaken, or even 2002. Already there, you could have removed essentially all the predictions for small chemical potential. So it was not the right plot, in my opinion, in the first place. Okay, so now I remove low energy effective theories, which have a critical endpoint at large density. And trust me, I have loads of computations here. Why do I do this? They miss quark-gluon back reaction. And if you go to chemical potentials of 800 or 600 mu B and you have a critical temperature of 200 MeV, you are in a combined external scale measure estimate of in the order of 1 GeV, and you definitely need quark-gluon back reaction. So you cannot benchmark your models here in the vacuum with vacuum results and trust results here. Okay? And again, keep this in mind, disclaimer, it does not mean I have also results here, but I don't use them for Z predictions. And I think nobody is doing this. Yes, the models have a critical endpoint somewhere. It's interesting to know it, because if you look at critical fluctuations, it's interesting to know where you get critical or not, but these are not Z predictions. Okay, so, I mean, you can say I designed it this way, but I didn't. I have also tossed out even a result here from beginning of this year, because we haven't had an update of the computation, and what is left are those 3 points. Okay, and those who are bang on the lattice curvature are those. So,
Jan?
Still, yeah.
So you have only 3 minutes left.
I know, but I'm essentially finished. So, yes, there are uncertainties, and I would say there are still uncertainties, and I would not call them larger. So this, for me, is not a larger uncertainty. This is something I can live with, and I hope that we will be able to get our hands on this in the next couple of years. Okay, so since I don't have any time, which I thought so, but I mean, you can also look at the rest of the talks in a quiet minute. What I would like to say are 2 remarks on the fluctuation of conserved charges. And before I come to this, I would like to say something which I call the unreasonable effectiveness of low energy effective theories. And so why do we expect that low energy effective theories are working well if I just have told you we need everything? The fact is that we have a sequential decoupling of gluon, quark, sigma, and pion fluctuations. So here what I'm plotting to you are the scattering couplings of quarks and gluons, light and strange. And then, if you wish, the coupling of the resonant interaction channels. So you see in the ultraviolet, the quark-gluon couplings are dominant, and then they decay rapidly, and the last one surviving, of course, is the pion. Okay, so you can see that if you're going essentially smaller than this scale here, you have a good chance in the low energy effective theory of your choice to get even quantitative results. So having said this, I would like to flash results on fluctuations of conserved charges in a so-called QCD assisted low energy effective theory, where we have used information from QCD flows for the setup of our low energy effective theory that builds on previous results, of course, and that's work in preparation with Xiaofeng Luo, Weiji Fu, Fabian Reinecke, and 2 students of Weiji in Thailand. Okay, so our lattice benchmarks, you see that our fluctuations are actually in line with the lattice results. And here we have our results for hyperfluctuations. I just don't want to say too much. These are our best shots. It depends a bit on the freeze-out curve you take. For the details, you have to wait for the paper. The only thing I want to say is the reliability of this QCD-assisted theory is here. Again, we have also given results here and they look good. But stay tuned for getting reliable results up to this point here, which is actually the mu b over t is 4, and that is work in process. Okay, I think I'm running out of time. Last remark, beware of the Taylor expansion. Here we compare Taylor expansion in our QCD assisted theory. So you see actually here it's compatible with the lattice result. These are the full results, and this is the Taylor expansion. So if you extend your results above a certain mu b, the Taylor expansion completely fails. Okay, so I spare you the transport, which I knew. So I hope I have convinced you that functional approaches, so I'm not only talking about the functional renormalization group, but also about Dyson-Schwinger equations, are going towards apparent convergence. So at large densities, we are not there. As I said to you, for mu b over t is larger than 4. We still have to do we still have to improve our approximations, and systematic improvements are currently underway. We have results and predictive power for the phase structure of QCD. My estimate is based on serious error investigations that we are good for mu b over t smaller than 4. We have observables, quark condensate, the phase boundary fluctuations of conserved charges, and now we of course want to resolve the region where potentially the critical endpoint is in. I have spared you the transport. This is my flash for these results, and I thank you for your attention.
Okay, thank you very much.